Okay, let's just start with the summit. So we have a special seminar because Frederic and Masset are invitee for the Jeffrey Funds defense will be passed with clearance, right? So that people know a little bit about Frederic. He did his PhD in Paget in
Exactly.
on galactic dynamics, spiral waves, and reactions, galaxies, and so on. Then he moved to Queen Mary College, London, where we overlapped for a year.
2 years.
2 years.
2 years.
And whenever I met Queen Mary, nobody would know what kind of this. So it's like, you know, and then he moved back to France as a CNR as a researcher. But the last 5 years he's been in Mexico. He won a lot of some French for the Mexico University for reason. He's been a professor there for the last few years. We're very glad to have you here because he's done some of the most pioneering work on planet migration, which so everybody in the field agrees is sort of one of the biggest roadblocks that's preventing us towards that planet migration. So I had the pleasure of reading some of your papers. Very interesting papers. So we're glad to be here.
Okay, thank you. Thank you very much for being here. Okay, so well, I will present briefly an overview of planet-disk tidal interactions. Planet-disk tidal interaction, as you all know, is a popular explanation to account for the orbital properties of extrasolar planets. It has probably not done the whole job itself. Other mechanisms are probably required to understand the huge diversity of the eccentricity semi-major axis statistics that we get, such as Kozai-Lidov effects and so on and so forth. But obviously a big thing is planet-disk tidal interactions. And understanding them requires a detailed knowledge of the disk, of the protoplanetary disk in which the planets are embedded, and a good understanding of the different processes that contribute to the tidal forces. So this is what this talk is going to be about, not so much of the first part, which we rely on observers for that, but on the second part. So in a nutshell, if you drop a point-like mass on a circular orbit in an otherwise unperturbed Keplerian disk, this point-like mass triggers a spiral wake in the disk, in the inner disk and in the outer disk. This spiral wake exerts a force in reaction on the planet. The planet no longer obeys the two-body problem, and therefore its orbital elements vary with time. The semi-major axis, its eccentricity and inclination vary with time. The most spectacular effect is probably the variation of the semi-major axis, which can be huge by orders of magnitude over the disk lifetime, and this is what is called the planetary migration. So this talk will focus on the effect of the disk on the semi-major axis. I won't discuss the variation of eccentricity or inclination. Okay, so in a bit more detail, the inner wake leads the planet and exerts a gravitational pull in the direction of rotation of the planet, hence a positive torque on the planet, whereas the outer wake trails the planet and exerts a negative torque. Because of the curvature, the planet location is not a point of symmetry for this pattern, so these two positive and negative components don't have to exactly cancel each other, and there is a residual. A slight imbalance between the inner and outer torque, the net torque. This is what yields the migration of the planet. So we have two huge torques, a small residual, which is not so small because it triggers a migration on a time scale which can be dangerously short. In the linear regime, when the planet mass is small enough, this should be an Earth symbol for some reason. When the planetary mass is below a few Earth masses, typically 10 Earth masses, we talk of type 1 migration. The net torque for historical reasons is called the differential because it's the residual between a large positive and negative torques. Lindblad torque, it's excited at the Lindblad resonances of the planet in the disk. And in the linear regime, this differential Lindblad torque is a negative quantity, and therefore the migration is inwards. Migration is inwards, and it is fast. If you drop a 1 Earth mass planet in a minimum mass solar nebula at 1 AU, for instance, it will reach the central object in typically 10 to the 5 years. Well, the exact value here can be the subject of some debate, but it's a short time scale compared to the disk lifetime, which is in million years. And more importantly, also it can be a short time scale compared to the build-up of a critical mass core, which can take of the order of a million years. Well, a critical mass core is a core mass such a solid core, such that runaway gas accretion occurs onto the core, and it should be quickly converted into a giant planet. So the giant planet build-up goes through this bottleneck stage of reaching the critical mass. Actually, the fact that the net torque is negative is not an obvious result. It seems like a fragile result because it comes from the imbalance between a large negative and a large positive torques. And therefore, we can imagine that by tweaking a bit the profiles in the disk, for instance, the density profile, we could achieve easily to reverse the torque. Say, for instance, let's take a very fast decreasing outwards, very peaked surface density profiles, so that inside of the orbit we have a lot of mass and less mass on the outer part. Then we weaken the outer torque, we enhance the inner torque, and so we should be able, maybe not to reverse migration, but at least to cancel it. It is not true, actually. There is an effect that frustrates this experiment. The drift rate is quite sensitive to the disk profiles. Assume, so that we take a very centrally peaked surface density profile. If we do so, we have a large radial pressure gradient in the disk, so it becomes, as we increase the slope of the surface density profile, the disk becomes more and more sub-Keplerian. And the wake excitation is a resonant process, into the details of which I won't enter, but it's a resonant process which occurs at fixed frequencies in the disk. So if the disk is rotating at a smaller frequency, then the wake should move inwards. And we can see that on this animation here, in which I show the perturbed surface density around an Earth mass or so planet as a function of the slope of the surface density profile. The positive slope means decreasing outwards. So you see that as the slope increases, we have this minute but apparent shift of the whole pattern rightwards. We also see that the contrast of the inner arm increases and decreases for the outer arm. Okay, so we have, this is what we were expecting, a stronger inner torque, smaller outer torque. Yes, but as the pattern moves rightwards here on this animation, we decrease the gravitational pull from this arm onto the planet, and we increase that of the outer arm on the planet. And both effects cancel each other. It's called the pressure buffer effect. And that makes the Lindblad torque essentially insensitive to the surface density gradient. The fact that migration is fast and inward is robust.
Is it somehow just cancel, or is it?
No, not exactly cancel, but the dependency of on the surface density slope is very small. Within the huge, totally unrealistic surface density to cancel the Lindblad torque. Okay, but in addition to this wake effect, we have also something which is linked to co-orbital dynamics and the horseshoe region. I'm not sure everyone here is familiar with the horseshoe region. So I just sum it up very briefly on this cartoon. We have here the inner solar system, the Earth, the planet are assumed to be on a circular orbit for simplicity, and we consider the trajectory of a yellow test particle here. The rotation is counterclockwise, and we are in the frame co-rotating with the Earth. So if we consider initially that the test particle is further out from the Earth, from the Sun than the Earth, then it is slower, Keplerian rotation, and therefore drifts in the clockwise. And so for most of its path, it will ignore the Earth, whose gravitational field is too weak to be felt, to be experienced. But when it reaches the vicinity of the Earth will exert on it a negative torque, because rotation is like this, and therefore it will lose angular momentum and its orbital radius will shrink. It will do so slowly, adiabatically, with no gain epicyclic eccentricity by doing so, and so it will experience a U-turn here, which is symmetric about the orbit. There is an invariant called the Jacobi invariant, which indicates that this U-turn to first order to the distance is symmetric. So once the U-turn is performed, now the test particle is closer to the Sun, faster than the Earth, and therefore drifts like this until it catches up the Earth on the other side. This time it sees the Earth in front of it, positive torque, and it gains the angular momentum that it had lost on the previous U-turn. And so on and so forth. The trajectory is is closed, and it has a horseshoe shape, hence the name. The same thing happens not to test particle in the restricted three-body problem, but to fluid elements in a disk in gaseous disk. You have here in red streamlines, so we have pressure in this problem in addition to the previous view graph, and we have a collection of streamlines which exhibit this horseshoe-like motion in the vicinity of the planet orbit. For most of my talk, I will represent this with the azimuth on the x-axis and the radius on the y-axis. So the horseshoe region is rectangular, essentially. Yes, this planet mass is not so small, and material is fleeing away from the co-orbital region, and so, well, I should have been more patient and run my simulations for days, and this would eventually be closed. Yeah. Okay, so on this side you have fluid elements that gain angular momentum from the planet and therefore exert on it a negative torque, and on the next horseshoe U-turn they lose angular momentum into the planet, they exert on it a positive torque. Now there is something which occurs when the planetary mass gets larger. The wake that the planet excites in the disk can be regarded in the low mass regime as a linear superposition of many waves excited at different azimuthal wave numbers. And it's not a shock, it's just a linear superposition of waves. It eventually shocks at some distance from the orbit. The smaller the planet mass, the further this occurs, if other damping processes have not damped the wake by then. But when the planet mass becomes larger than some threshold, typically when its heel radius is comparable to the vertical scale height of the disk, the pressure scale height, then the wake becomes a shock even in the vicinity of the planet where it is excited. And in that case, it's very easy by using the Rankine-Hugoniot relationship across a shock. We say that the normal velocity is smaller after the shock, and the tangential velocity is the same. It's very easy to see that on this side of the shock, the fluid element will gain angular momentum, and on this side of the shock, they will lose angular momentum. So this can be seen here for the C2 fluid element, C like circulating. It will be promoted to a higher orbital radius after crossing the shock. And vice versa, the C1 fluid element here will lose some angular momentum after the shock. By continuity, there is this region here. We are just across the separatrix, the boundary of the horseshoe region here. So we have here a librating fluid element, L1, which will perform a horseshoe U-turn, but it cannot do so in a symmetric fashion. If it did, it would arrive here, and we would have here a completely empty region. Its empty region is filled up by pressure forces. And the horseshoe U-turn is not symmetric. This librating fluid element lies further from the orbit after the U-turn. And the same is true of this on the other side. This L2 fluid element here goes further in. So every time a fluid element of the horseshoe region here undergoes a horseshoe U-turn, a U-turn in the vicinity of the planet, it gets further and further away from the orbit until it arrives either in the inner disk or outer disk. And that empties the horseshoe region over a time scale of a few libration times. Arguably, as we discussed earlier on today, this could also happen at weaker planet masses, smaller planet masses, provided at some point this wake become a shock. So it becomes a shock in where it is excited when the planet mass is above this thermal mass for which the Hill radius is equal to the pressure scale height, and it will occur beyond that at larger distances from the planet when the planet mass is smaller. Okay, so this animation here shows you how a gap is opened by a 1 Jupiter mass planet. There is no gas accretion here on the planet. It's purely tidal, and this occurs on typically 10 to the 2 100 orbits, which amounts to a few horseshoe libration time scale for these planetary masses. Okay, so there was this common wisdom in the field that migration with gap is called type 2 migration, and that type 2 migration is locked in the disk viscous evolution. The reason for that is, okay, the planet tidally truncates the disk in two parts, the inner disk, the outer disk, and okay, let's get rid, I thought, of the inner disk. It has a short accretion time scale onto the star. Let's assume that we just have the outer disk tidally truncating and the planet. So we only have the outer wake, which exerts a negative torque. The planet wants to move here. But if it does so too fast, it loses contact with the disk. It has to wait for the disk to follow it. And the disk can only follow the planet at its own pace, which is the viscous drift rate. And so instead, in a steady state picture, the disk and the planet will move inwards at the viscous drift rate. So that was, let's say, the big picture. There is a growing body of works and numerical evidence that say that, well, it's not so true. And actually, the migration of large planet masses is at a smaller velocity than the disk viscous drift rate. There is even a paper recently, I think, by Duffel, whose title is Type 2 migration is not locked in the disk viscous evolution. It's very explicit. So there is a shift of paradigm away from this old wisdom. Okay, so this is with very exaggerated parameters to emphasize the transition from type 1, low planetary mass, fast migration, to gap opening and slowdown of migration and type 2 migration. Regardless of whether type 2 migration is or not locked in the disk viscous evolution, by far the most threatening stage is type 1 migration, which is really fast. Type 2, locked or not, is much
this information, the spiral wake is clearly going away completely as from type 1 to type 2 migration. In the previous animation, even though the spiral, in the previous animation,
this one,
even though the spiral wake weakened, it was still there. There was still a spiral wake. So
on this one, there is still oh yes, it's because there is a difference between. I have accretion turned on in the next, and that takes away all the material that could contribute to the beginning of the wake. Yeah.
And this is the difference. What was the difference?
Sorry. So on this one, the wake goes all the way to the planet and reaches it. Yeah. And whereas in this one, once the planet is a giant planet and you have a gap, here it's essentially, it disappears. But this is because of the course. Yeah. Yeah. It's because of the accretion prescription that I used to make this animation.
There's no material crossing across.
Here, remember that I have very irrealistic parameter to catch in 200 orbits a transition from type 2 to from type 1 to type 2, so it might not be realistic. Yeah. Thank you. Okay, so there have been a bunch of criteria for gap opening, in which, well, if we want a gap sitting near the planet, we would need the thermal criterion to be satisfied. The planet must be above some threshold to allow the wake to be a shock in its immediate vicinity. And beside this criterion, the tidal forces tend to evacuate the co-orbital material, and the viscosity tends all the time, it counteracts the action of the tidal forces and tends to fill up the gap. So there is an antagonism between these two agents, and which, well, we can write a unique criterion for taking into account both the tidal forces and the action of viscosity under this shape. Well, there has been different flavors of it, but they all amount to these two conditions, basically. By 3D simulation, systematic 3D simulation, which would explore this set of parameters, I don't think so. No, it's really a good. We don't know. No, I'm not. I'm not sure how sensitive the boundaries of this domain are to 2D versus 3D. Okay. Now, so the material which is on the horseshoe streamlines contributes, as I said, to a torque on the planet, which is called the co-rotation torque. It's an easy matter, by the way, to realize that on the average, the angular velocity of a fluid element or horseshoe fluid element is strictly the same as the angular velocity of the planet, because it never passes the planet. It's like two runners on a stadium, and they are never at the same azimuth. They have the same average angular velocity. Not necessarily linear, by the way. Okay, so I will come back in a minute why this quantity, but for now, I just state it and ask you to believe me. The key quantity here, which drives the co-rotation torque, is the vorticity. The vorticity is the ratio of the vorticity of the flow, vertical component, divided by the surface density, which is dubbed vorticity in astrophysics. So we assume that, well, actually, I consider it's inverse, so surface density divided by the vorticity. This B constant, for who know, is the second order constant in the flow vorticity. So there is a factor of 2. So assume that we have more vorticity on one side of the orbit. So these fluid elements will give a large contribution to the co-rotation torque, positive contribution on this side, remember? And you have less vorticity on the other side, so these, as they drift and execute their horseshoe U-turn, will give a negative contribution, but smaller in absolute value. And therefore, the net torque can be seen as depending on the gradient across the orbit of the vorticity, the radial vorticity profile in the disk. It is usually too weak in a disk which has power law profiles to counteract the differential Lindblad torque, and especially in the linear regime. A very hand-wavy, very hand-wavy view graph to give maybe some insight as why the vorticity is conserved in a barotropic, two-dimensional inviscid flow. Assume that you have a cylinder here which has some surface density or column density, sigma, given mass, and a given spin rate, omega, and a given radius. And for some reason it contracts and its radius becomes r/2, the conservation of the angular momentum. With the new moment of inertia that it has, it dictates that it has to rotate 4 times faster. And its surface density is also 4 times larger. So the ratio of sigma over omega, or the inverse, is conserved. And you can probably regard the fluid elements in a 2D barotropic flow inviscid, because we don't want them to experience viscous stresses from their neighbors as these small cylinders. And this is a property, well-known property, an avatar of the Kelvin theorem. The vorticity is conserved in a 2D inviscid barotropic flow. And so, well, the contribution of the horseshoe region to the torque can be expressed as a famous integral called the horseshoe drag, which involves therefore the calculation of I won't enter into the detail, but an integral over the width of the horseshoe region only of some function related to the vorticity. Note that it's not the vorticity per se which exerts the torque. Naturally, it's the density, but on the density you see nothing in a barotropic disk. Why is that so? Because you cannot concentrate the mass like you would concentrate the vorticity. You have evanescent waves in this region which smear out any localized surface density that you may try to build radially over a pressure scale height. Okay, but even if you don't see the perturbation here, we see a hint of it, but it's very diffuse. We can account for it by looking at the much more concentrated and bound to the horseshoe region vorticity distribution.
Sorry, what does this figure say?
So, okay, here we have the vorticity distribution and associated surface density distribution. Yeah, yeah. So, in a barotropic disk, there is a one-to-one relationship. You have, if you have a narrow localized Dirac delta function of vorticity, it is associated to something which is in exponential minus absolute value of x over h, like yes, two evanescent waves sitting on each side of this discontinuity of vorticity. And now for a general distribution of vorticity, the surface density, the perturbed surface density associated to it is a convolution of this vorticity distribution by this kernel. Okay, so is the convolution of this by this. If you were to use the density to account for the co-rotation torque coming from this region, you would have to integrate further out than the horseshoe limits because of this mirroring out. But you don't have to bother with that because you have a handle on. You can reconstruct the surface, all this contribution by just having a look at the vorticity, which leaves a localized imprint. And so you will restrict your horseshoe integral just over from separatrix to separatrix, no beyond.
Hence the only change near the planet.
Yeah, yeah. The vorticity is advected. So here this is the perturbed vorticity, the vorticity minus the initial one. So you had here advection like this, which gives say a positive lobe if you had a negative gradient, and on the other side it gives a negative lobe. Okay, just by pure advection. Okay. One reason why the co-rotation torque was for quite some time neglected in analysis of planetary migration is because it saturates. So the picture associated to this realization, to this population of vorticity positive gradient, is that we have a positive torque, as I said, coming from this blue streamline. But when these elements and this one have swapped their position, then we will have more vorticity on this side and less on this side, and the torque will be reverted like this. And for the next half libration time, horseshoe libration time, the torque will be negative, and so on and so forth. For the red fluid element, now we will get the same picture, but smaller jump, smaller horseshoe jumps, so weaker torque contribution, and larger libration time, because the closer you are to the orbit, the longer it takes to perform a libration time. So it will give you something like this. And you get obviously phase mixing, and the net torque is something which decays over a few libration times and tends to zero. It is said to saturate. as the result of phase mixing. And that amounts to the fact that you don't have waves which go out of this region. So the angular momentum of the horseshoe region plus the planet is a constant in time. And so the net angular momentum ever exchanged between the planet and that region can only be finite. And so if you average this out of a large time scale, then you get a zero average torque. Okay. The only manner you can one manner you can counteract this is by having viscous diffusion in your disk. So this little toy animation on the left shows the vortencity. So we have which undergoes horseshoe U-turns on one side and on the other side. So this is sent here. I don't resolve the U-turn here. It's just a mirror symmetry on this side and on this side. So you get advection like this, which steers the vortencity across this region, and on the long term cancels its gradient. It flattens it. It flattens out the vortencity gradient across this region, and this famous horseshoe drag integral that you can perform here shows a net torque that tends to zero. This would be in the low viscosity regime. But if now you have a large viscosity, the large viscosity will act to restore at an instant in time the large scale gradient, and it will prevent this complete flattening out of the profile. You will keep some gradient of vortencity across that region and a finite co-rotation torque at larger time. Okay, so basically this toy model of advection that I've just shown, of the advection and diffusion that I have just shown in the previous view graph, plus some viscous diffusion, gives this torque behavior as a function of time. Now, the full simulation, hydro simulation with viscosity, planet, and so on and so forth, gives this torque behavior as a function of time. Here, different colors show different viscosities. Reddish is for nearly inviscid disk, up to very viscous disk on the purple side of the spectrum. Okay, so and it gives satisfactory dependence on the torque as a function of viscosity. So this is a parameter related to viscosity. Diamonds here are for numerical simulations, and this solid line here is for the analytic description that comes from this model. Now this is with a very simple description of viscous effects. We take just a laminar viscosity. In reality, the effective viscosity that is at work in protoplanetary disk is thought to be of turbulent origin, probably the consequence of the MRI. So what would be the results, the equivalent results to what I've just shown in case of a true turbulence? Well, there is an intermediate answer to this question in which Barito and Lin have had a hydro disk, no MRI, no MHD, but they had a stochastic potential terms which would not experienced by the planet, but felt by the gas, which would in 2D would mimic a turbulent regime, and they would average out the torque value over large periods like this and monitor the torque as a function of the effective viscosity. So the laminar calculations with the same effective viscosity would give that, and the turbulent case would give something similar, although with a stronger cutoff at larger effective viscosities. Now this is just an intermediate answer. What would be the case with turbulent MHD simulations? That's much more expensive to study because we need the third dimension. It's relatively difficult to vary the effective viscosity. You can play with parameters, like the beta parameter of your plasma and so on and so forth, but it's very touchy. It's difficult to gradually tune the effective viscosity in these simulations. You need to get proper time average, so you need to do simulations over very long time scales over which the disk profiles strongly drift usually, so you would need to repeat many simulations with different random seeds, and that's very expensive. And there are probably additional effects due to the magnetic field, which have been captured in this 2D analysis by Gillett et al. In 2013, in which they see that the magnetic toroidal magnetic field gives rise to a new co-rotation torque component. So really, the full picture in magnetized turbulent disk is different from the time average of the laminar situation. Has a time average different from the laminar situation.
What does that figure actually say?
Oh, sorry, it's a figure extracted from that paper, in which we consider different laminar disk with different alpha values, and we try to find the alpha that best matches what we get for the torque in a turbulent disk. With this time average, running time average values of the torque, I guess.
The torque changes sign.
Sorry?
The torque changes the sign. We can give an alpha?
Yes. Yeah. In that case, the net torque is positive.
Or net torque?
Yeah.
Not the co-rotation torque. It's a net.
Yes, it's a net. It's lambda plus co-rotation. Okay, so let me present a situation in which the co-rotation torque can play an important role. As I've said, it scales with the gradient of the vorticity across the orbit, and the vorticity is the vorticity divided by the surface density. So whenever we have a large gradient of surface density, we may expect the co-rotation torque to be boosted. That would happen, for instance, at the inner edge of a disk, at a cavity edge, in which the surface density gradient can almost be arbitrarily large. We expect this not to be smaller than the disk pressure scale height, otherwise the disk becomes unstable. But this gradient can be made large. And so here on that side you have many fluid elements losing angular momentum to the planet and not so many gaining angular momentum from it. So a net large positive co-rotation torque. So if we do a back of the envelope calculation of what we can gain like this, in a power law disk, let's call 1 the -1, the differential Lindblad torque, because it's negative. The co-rotation torque in a flat surface density disk will be at most half of it in absolute value. So we get a negative net torque. At a cavity edge, well, there is bad news. We don't have anymore a differential Lindblad torque because we lose the inner torque. We are at the edge of a cavity, so we only have the outer torque, which is strongly negative. We don't have the residual value. We have the full. We receive the full negative torque of the outer wake. So if you put figure on this, you can see that it can be up to 4 times larger. But the co-rotation torque will scale with sigma, not the slope of sigma. At first approximation, it should be the slope of vorticity, but let's say it's sigma. And it can be the sigma can vary significantly over a scale as short as h. So we will boost what we would get in a power law disk by a factor of r over h typically. And h over r in a protoplanetary disk is a small factor, typically 5%. So let's be conservative. Let's assume it's a thick disk, so we gain only a factor of 10. So we would get +5. And you see that by being conservative, we may expect to get a positive net torque at the cavity edge because of the large boost of the co-rotation torque, despite the fact that we lose the inner wake torque. And so we can test that. We realize surface density jump somewhere in a disk. It looks like this. And it turns out to have this in arbitrary unit gradient of vorticity, the quantity with which the co-rotation torque should scale. And if we put different planets in different runs at different orbital radii and measure the net torques exerted on these planets as a function of their radius. We see this. So here, at larger radius, negative, the standard type 1 negative torque. Then some strong bump here, and virtually no torque inside the cavity. And well, I think it's not an overstatement to see that these two curves look alike. So we see here a signature of a strong rotation torque at work, and we see a fixed point here in which the torque cancels out. This fixed point is 0 because it moves the planet outwards. It feels a negative torque, which brings it back to a fixed point. And the same is true on the other side. It's a fixed, stable point. And we can just drop planets at this radius in the disk and let them freely decay toward the cavity edge at a pace which will depend obviously on their masses, but they all eventually get trapped at the fixed point location we just saw on the previous view graph. Okay, and so if the cavity expands or contracts as time goes on, for instance, assume it expands, if the planet stays in place, it will feel a positive torque. If it feels a positive torque, then it will move outwards and it will follow, provided the expansion is not too fast, it will follow the edge. So the cavity edge traps the embryos. So what kind of cavities can we think of for that? The inner edge of a dead zone, I know the mere existence at this precise time of dead zones is in jeopardy, but if they exist and they have an inner edge, at the inner edge we presumably have a drop of surface density. The transition between a standard accretion disk and a jet emitting disk solution at shorter radius, although the simple picture of the previous view graphs is more complex because we have magnetic field. A disk truncated by tidal effects. So either the outer edge of a gap or a disk which is truncated by a binary star inside. And note that in this whole picture there is some degree of turbulence or diffusion that is required to prevent the saturation of the rotation torque.
The third point, if it's the previous slide.
Yes, sure.
So something is maintaining that sharp density that you want to get a large rotation torque.
Exactly. We want to maintain this.
You maintain it very steep.
Yes, you want to avoid saturation. You want diffusion to achieve, to restore over a time scale shorter than the horseshoe libration time this gradient, otherwise you do saturate and yeah.
But if you use things like tidal effect, meaning this is the third case.
Oh yes, tidal effects here. You need some diffusion, some viscosity here.
That's got to work on the co-rotation material too. If it's working on the disk to keep the edge very sharp, if the tidal effect so strong at the edge boundary
Yes.
to keep the density sharp, that has to work. That force also works on the horseshoe orbit too.
It's
the novel analysis.
so it's the horseshoe orbit of some embedded small mass object at the edge.
Right.
Yeah.
It's not clear that.
It's not clear, but it has been checked by numerical simulation by these authors that they do get a stalling of migration at this.
I see. So you do not perturb the horseshoe orbit enough.
Yeah. Okay. All what I've just presented in the previous view graphs, migration trap will work only if the planet does not destroy does not cut the branch on which it is. Okay, so if its mass is small enough so that it does not evacuate the horseshoe region, if it does not clear a gap. If it does clear a gap, then it has nothing to prevent migration, it will carry on until typically it will be in 2-to-1 mid-motion resonance with the cavity edge. Further out, there is no, further in, there is not much torque left to push it more inwards. And we have seen that with numerical simulations. By the way, we see a transition. This is the stopping radius in numerical simulations as a function of planetary mass for a 5% aspect ratio disk. And we see that we have this very neat change of stopping orbital radius at 1 Jupiter mass, and this is reminiscent of what is seen in the distribution in orbital statistic of extrasolar planets. We have a drop here near 1 Jupiter mass of the planetary periods. Well, this can be due to a variety of effects, but that could be one of these effects.
But there are low mass planets which are present as well.
Yeah. On the other, well, you know, there are a large variety of effects. Yeah. But yes, but this void is significant. I mean, there is a drop here. If at a given period band here, you draw the statistics of you have a drop here. These objects are mostly prevented from going further in, and these ones, there is a sharp dependency here. This is almost a staircase.
Yes, I agree with you. There's a problem there.
Yeah. Okay. So I think I should speed up a bit. Started late, but okay. So for the time being, I have only presented what happens when you consider the torque on a planet on a fixed circular orbit. Now assume that the planet is migrating. So the planet in blue here and the fluid element in red. The dotted lines show the separatrices of the horseshoe region. Initially, this fluid element has some angular momentum, highest orbital radius, and when the planet when it enters the horseshoe region of the planet, it performs one unique horseshoe U-turn and goes out on the other side, and it has thus gained angular momentum with the planet. It has taken away this angular momentum from the planet. During the unique encounter, this fluid element exerts a negative torque on the planet. Okay, so the fact that the planet migrates inwards has a consequence that the fluid element that goes from the inner to the outer disk exerts a negative torque on it, and the faster the planet will migrate, the larger the mass rate of this inflowing fluid element will be, and therefore the more negative will be the torque. So we see here we have the seed for a feedback loop, positive feedback. More negative the torque, the planet migrates faster, and so on and so forth. But we have also another effect which comes from the horseshoe region, which acts like a cage, a trap for the fluid elements. In between two encounters here, two horseshoe U-turns, the fluid element has a horizontal trajectory. Therefore, it conserves its angular momentum. But because of the drift of the planet, you can see that the jumps here on this side are larger than the jumps on this side. So this means here it exerts a positive torque larger than the negative torque on the other side. So the fluid element exerts in average a positive torque on the planet, action and reaction low. The horseshoe region exerts the horseshoe region exerts a positive torque on the planet. So that means negative feedback. The faster the planet will migrate, the larger will be the difference between these two jumps, and the more positive will be the torque. This is a very this can be expected from first principle. As you see, this material in the horseshoe region is trapped, so the planet forces the whole horseshoe region to lose angular momentum at the same specific rate as it does, and so it exerts on it a negative torque, and action and reaction low, this region exerts a positive torque on the planet. So negative feedback. So we have two feedbacks, one positive, one negative, and if the disk profiles are unperturbed, then the two effects cancel each other. which makes sense. We have material flowing on one side, flowing on the other side. If there is no specific perturbation of the disk profile, the planet does not care whether this material comes from the inner disk or the horseshoe region. It just sees this symmetric horseshoe U-turn and no net torque. But if the planet begins to deplete its horseshoe region because it has a sufficiently large mass for doing so, then we weaken the negative feedback of the horseshoe region, and the net feedback is a positive one. So that will occur for planets which can deplete at least partially the co-orbital region, giant planets. So a schematic picture, we have the net torque, which is the sum of the Lindblad torque and the co-rotation torque. And the co-rotation, so the total torque gives the drift rate, and the drift rate has a back reaction of the co-rotation torque. So we have a feedback cycle here. So we can work out, and so every time you have positive feedback, not necessarily do you have a runaway. The feedback needs to be strong enough for the cycle to run away. Typically, it occurs when the gain of the open loop, if you cut here, and and you have a signal here and another signal here, the runaway will occur if this signal is larger than this one. The open loop gain must be larger than 1. And it's the product of A by B here. It's easy to see that it will occur if the what is called here delta M, the co-orbital mass deficit, the mass that is lacking in the co-orbital region, is larger than the planetary mass. Then in those cases will you get a runaway of the migration. In a planet mass, disk mass plane, this will happen in this gray region. So small planetary mass type 1 migration, large planetary mass type 2 migration, transition region. Here we have very massive disks, so gravitationally unstable. And this region would be where you would get runaway migration. Note that a Saturn mass planet in the minimum mass solar nebula at 10 AU is on the limit of that. So Saturn presumably has been very mobile at some point in the... Okay. Naturally, this dependency on the torque, on the drift rate, saturates. When the migration is fast enough, faster than it takes for... when the planet migrates over a distance that is larger than the horseshoe width in less time than it takes for fluid elements to liberate in this region, the feedback saturates. We have this linear dependency on the torque at small drift rate, but you have a plateau phase here at larger drift rates in absolute value. So if you start with a planet, so this is the torque as a function of the disk torque as a function of the drift rate, and this is the rate at which the planet loses angular momentum. And in steady state, they have to coincide. So let's imagine that you drop a planet initially in fixed circular orbit in the disk, so it will feel this torque, and therefore will get this drift rate, at which it will feel this torque and get this drift rate, and so on and so forth, until it goes, well, it goes here directly, but it could go like this up to this fixed point, or if I had managed to start in the other direction, it could have run away to reached this fixed point on the other side. Okay. So actually, the intersection of this line with the torque curve depends on how massive the disk and the planet are. Here I will vary the surface density of the disk at fixed planetary mass, and this is what we get. At some point, we have 3 intersection points and 3 possible drift rates. The unique, the central one is unstable, as you can see from the previous view graphs, and these are stables and corresponds either to inward or outer migration, and you have here this unstable solution. So if you start above it, you will run away outwards, and inside of it, you will run away inwards. So this is no migration at all initially, so you would start underneath the green curve and you would run away inwards. So you have basically a very rich variety of outcomes from runaway or type-free migration. I would say that the runaway migration is this initial stage, and when you get to these curves, it's that type-3 migration. So this would be an animation of a runaway migrating Saturn, and you see this very asymmetric co-orbital depletion here on the front side of the planet. So this has, at some point, Pavel Artemovich said that the planet was surfing on vacuum. This is the co-orbital mass deficit here in real space. Okay. In what, how much time do I have left? Very few minutes? Okay, so I would rather skip this dependency on the co-rotation talk on the thermodynamics of the disk. But I would like to mention that the co-rotation talk also depends on the thermodynamics of the disk, and quite strongly actually. And this has, I will present this in a, no, hold on. In a recent work, we considered whether the heating due to the planet by being bombarded by planetesimals would heat the surrounding nebula with possibly a significant impact on the torque. So I will go very, very fast on this. I will just incorporate the heat release by assuming a physical radius of the planet and a bombardment rate, and therefore energy is released in the disk at this rate, which assumes that all infalling bodies reach the planet's surface. Well, you can try to see whether this is true. These are low mass planets. Earth mass also a bit larger, a few Earth masses, so they have a tiny envelope. So planetesimals should reach the physical radius of the planet. Pebbles, maybe barely so, but the assumption, this simple expression is relatively well grounded. Okay, so we solved the hydrodynamics equation on a spherical mesh. We solved the radiative transfer equation in the Gray approximation and flux-limited diffusion with a two-temperature approach on this mesh. And we start with a disk which is both in thermal and radiative equilibrium, the internal energy source for the disk being the viscous heating. And we release the heat in the cells that surround the planet. The planet is at a corner between cells, so it has 8 neighboring cells, and we release the heat in them. And as we release the heat, we see that the more heat is released, the more positive is the torque. This is in the no heating, the neutral case. The torque is negative, but by shortening the mass doubling time of the planet, we get more and more positive values of the time average torque. And basically, we get a torque reversal for a mass doubling time smaller than 100,000 years. So where does that come from? We have, it's an advection and diffusion problem. Basically, we have, so the disk maintains its pressure equilibrium. So wherever it is hotter, it is less dense. The planet releases heat here, which diffuses under the equations of radiative transfer, and which is advected in the sheared Keplerian flow. So it goes like this, and it diffuses. Okay. So this is what we would, the same picture for the very same parameter, in the case in which you don't, with the same color palette and mean and max values, in case you don't get heating. So you see the dramatic impact of the heating. You have dark lobes. You have more empty regions as expected because it's hotter. Okay. So we have 2 underdense lobes on each side of the planet. Now, okay, in an idealized situation in which you have a uniform density, you have no net force. In the case in which you have an underdense region on one side of the planet, you get a net force opposite of it, like a negative mass, in quotation marks. Okay, so why is the torque positive? It is because this is very apparent on these view graphs here. The left lobe is more pronounced than the front lobe. It's wider and the density goes down to it's darker here. This is very apparent. So a stronger force like this than this one, and a net contribution that is positive. Now, why do we get? Why is that so? Why the question can be recast as why is the rear lobe more pronounced? Actually, it's the fact that the disk is sub-Keplerian, so the co-rotation is a bit inside of the planet orbit. The planet is on this side of co-rotation. You have advection this way under co-rotation and that way under above co-rotation. And the planet is on the side that goes to the left, which receives more heat than the side that goes to the right. And if you work out the value of the heating torque, that is the torque with heating minus the torque without heating, the net effect due to heating as a function of the surface density slope. And so when this value is very negative, you get a positive radial pressure gradient, and therefore something which is a bit artificial. You get the co-rotation outside, and the heating torque is negative. But for most of this, for realistic values of the surface density gradient, the co-rotation is inside, and you get a positive heating torque. So this picture is in complete consistence with our interpretation of the fact that the planet releases more heat on one side or the other side, and that determines the ultimate sign of the heating torque. Okay, just a takeaway message from this. The heating torque scales with the mass doubling rate, with the mass accretion rate, and therefore it scales with a solid content in the disk. If the solid content is higher, you have a larger bombardment rate on one hand. On the other hand, it also depends through the opacity with the disk metallicity. If the disk is more opaque, the heat is more accumulated in the vicinity of the planet, and the heating torque is stronger as well. So there is a twofold dependency on the disk metallicity. This torque scales very strongly with metallicity. That's the first takeaway message. The second one is that this torque, this heating torque, a priori would not have been expected to have same order of magnitude than the standard wake torque. The wake torque depends on the surface density, the temperature of the disk, planet mass. The heating torque depends on the bombardment rate, on the planet physical radius, hence on the solid density, and so on and so forth. So it's a serendipitous coincidence of the orders of magnitude of the torques, which makes it very interesting. So we probably have a bifurcation depending on the metallicity, under which we still the dominant torque is a wake torque, and above which we get a migration reversal due to the heating torque. Okay, well, I come back to the previous.
Can I give you 1 minute to summarize?
It's my conclusions. So the theories of planetary migration have considerably evolved since the standard paradigm of inwards and boring migrations, type 1, type 2. The co-rotation torque has recently received, over the last decade or so, a lot of attention, and it has been shown to play a crucial role in several regimes of migration, like type 3, planetary trap, radiatively inefficient disk that I didn't have time to mention. Type 3, by the way, has been extended recently even to lower mass objects. At some point, people get annoyed by planetary migration, saying it was overrated. And that observers in particular, and well, there were publications in which people lower the type 1 drift rate in planetary model of planet synthesis by a factor of 10 or 100, and say that they can reproduce observational statistics. So I say, well, maybe planets don't migrate at the end of the day. So at some point, people got tired, I guess, of planetary migration yet. I hope I have convinced you that, well, the planet is subjected to very large torques, which do not exactly cancel, and the residual is large, and the determination of the residual demand accurate derivations and a fine-grained knowledge of the disk properties, which is, I guess, is still beyond the state-of-art of observations. So my belief is migration theories are not overrated, but they are only slowly maturing. Okay, so please ask if you have any questions.
In between the type 1 and type 2 regimes, so the type 3 regime,
yes,
but for an automass like this,
yes,
not a runaway regime,
yeah.
Does that just mean your planet is more massive than the thermal mass?
Yes.
But hasn't opened the gap yet?
Yeah.
Can you say anything generic about migration rates in that regime?
In that regime, yes. So the migration is aided, is helped by the lack, by the co-orbital mass deficit. So it would actually migrate as if the mass of the migrating object was the planet mass minus the co-orbital mass deficit, which by definition is smaller than the planetary masses, because this is the regime you are interested in. So it will give you a drift rate which is marginally faster than if you didn't take into account these type 3 effects. Yeah.
Well, with that, should we thank the speakers? So Frederic is going to be around.